Hi, I'm Shirley. I'm a PhD student in Stony Brook University. Today, Joseph from Oak Ridge National Lab and I are going to present our ongoing work, LTO and JIT support in LLVM OpenMP target offloading. So I'm going to introduce the JIT support, and Joseph will talk about the LTO support. We will use NVIDIA toolchains as example here, but the design also applies to another targets. In current OpenMP offloading compilation flow, after we get the PTX from LLVM backend, the clone driver will call PTX-AS and NVLink to generate the device image, which is bundled to host code to get a fat binary. During the runtime initialization, CUDA driver API is called to load the device image. When the target region is executed, the corresponding kernel entry will be passed to the driver API to launch the kernel. Since there are always information unavailable in compile time, in addition to fine designed middle and optimization to deduce more runtime information, it's also ideal to use Jit compilation. Next, please. In order to do that, we directly embed the device IR into a host binary, and in the runtime, only load the image when a target region is executed. LTO module is used here because it comes with full middle and backend. After an LTO module is created from buffer, it will be modified with runtime info, such as kernel arguments. After that, we use LTO code generator along with the device info to optimize the module and generate PTX. Next, we load PTX using CUDA driver API along with options collected from runtime and device info, such as the maximum number of registers that a thread may use. We also cache the image such that we can directly launch the kernel if the same setting is encountered. Currently, we have a working prototype, and we are still improving it. At the same time, we plan more optimizations. That's it for JIT. Now hand over to Joseph.
Okay, so why do we want to support LTO and OpenMP target offloading? So what we want to do is have a single target offloading method that we can specialize to whatever is efficient for whatever target architecture you might offload to. So for example, with this code, if you offloaded to a GPU target, the teams would bind to the blocks on the GPU and the parallel would bind to the threads. In this case, you'd have this single thread only region would be called by just a single thread in each block, which would then fork off parallel work and then execute all threads on this stack allocated variable. Now, we want to turn this into the bottom code, which is more efficient when executing on a GPU target. We want to remove the overhead of launching the parallel region in the middle of this, so we want to have the parallel region activated through the entire target region. And we can then execute that single thread only region by just using a mask on the thread ID and then performing a barrier to synchronize all the threads. This is similar to how CUDA does their kernels. And this stack variable, we want to make sure that it's private to each thread so that the allocation can stay inside the register file on the device. So we can do these optimizations, but only if we have enough analysis using interprocedural techniques to determine that this is legal, because the OpenMP standard allows people to do many kinds of things that would invalidate this transformation. For example, in the single-threaded region, they could call nested parallelism or do some optimization that couldn't just be simply masked away like this. And in the working function, they could take a copy to that pointer, which OpenMP allows them to do, and then store it and share it between the threads. So in order for us to make this transformation, we need to have full visibility of these functions, or else our interprocedural analysis just completely stops. So this is where LTO comes in. With LTO, we can put this into a single module that we have complete visibility of these functions, and everything is internal and needs to be internal, so we can have an ideal position to start with our interprocedural optimization. So this is an overview of how we're going to be handling link time optimization when compiling for target offloading. So the standard LTO pipeline takes each input file, compiles it to an LLVM IR bitcode file, runs optimizations on it individually, and then sends it to the linker. The linker will then take each input file, scan for any files that include LLVM bitcode, combine those into a single module, run optimizations on that whole module and then a backend on that, and then give it back to the linker. So our work is mostly building off of this architecture already, with a few differences, that being we get multiple input files, we get multiple bitcode files from the input, and we need to run two separate compilation paths in the LTO module. So when we take our input file, we get a device bitcode file and a host bitcode file. We can run optimizations on these individually, and then when we combine them into a single object file using an archive bundling tool. These are then sent to the linker, and then the gold plugin, which we used, will scan all of its input for something that contains an archive bundle. If it finds an archive bundle, it will then take out the host and the device bitcode, and we will combine these into separate modules, one for the host and one for the device. The host LTO module will run as I described before and then get sent back to the linker. The device will run similarly, but we'll need to run the vendor backend on it to get a final binary image for the target region that we can embed into the host code that is put into the FAT binary. If we're using JIT, then we can bypass this step and just embed LLVM IR, which will then be JITted, as Sheila explained. So this is our work generally, which should be done by LLVM 14's release, which will allow us to specialize kernels for their specific arguments with JIT and have complete visibility of the code, allowing users to use standard LTO without interrupting their compilation flow when doing OpenMP offloading.